Now come to the today's topic. RL series circuit is excited by a step response of V volts. Under transient behavior, we are calculating the current flowing through the circuit. At t is equal to 0, the switch will be closes. Okay. So at t is equal to 0 means, so you have to consider the two conditions. At t is equal to 0 minus and at t is equal to 0 plus. So what is t is equal to 0 minus? The switch just before closing position. And what is t is equal to 0 plus? The switch is immediately closed position. Okay. So now at t is equal to 0 minus condition. So what is the current flowing through the circuit? No current will flow through the circuit. So the current in the circuit is 0. Still it is open path only. Then immediately the switch is closed position at t is equal to 0 plus. The inductor never takes the instantaneous currents. So it never takes the instantaneous currents means it is open circuited. So under that condition, so I of 0 plus is also 0. So these are the two initial conditions we are getting when the switch is closed at t is equal to 0. So now I am applying the KVL for the RC circuit. So R into I plus L di by dt is equal to V. So then I am taking di by dt plus R by L into I is equal to V by L, or capital D plus R by L into I is equal to V by L. So this is your first order differential homogeneous equation. It is also a first order differential homogeneous equation. So to go for the solution, so one thing is d plus r by l is equal to 0. D plus r by l into I is equal to 0. So you can get a general solution that, so the transient behavior value will be a into e power minus r by l into t. A into e power minus r by L into t. So for finding the particular integral, so we are going for d plus r by L into I is equal to V by L, or I is equal to V divided by L into d plus r by L. Okay. So the L is multiplied. The L is multiplied in the denominator term d plus r by L. So L is a fixed value. So if you multiply by d, what is d? D by dt. So the constant value is multiplied or differentiated, then you can get 0. So finally L into r by L you can get. So L and L gets cancelled. So you can get I is equal to V by R. So this is your particular integral value. So it is also a steady state value. And the complete solution is your steady state value plus transient response value. So V by R plus A into e power minus R by L into T. Okay. So now for finding the initial value, for for A, so I am substituting t is equal to 0 plus condition. So what is t is equal to 0 plus condition? T is equal to 0 plus condition. So your I of t, your I of 0 plus is 0 only. Is 0 only. Are you understanding? So I of 0 plus is 0 only. So from that we are substituting I of 0 plus is equal to V by R plus A, e power 0 is 1. So A only. So that implies 0 is equal to A plus V by R, or A is equal to minus V by R. So therefore substitute in the complete solution equation. So I of t is equal to V by R minus V by R e power minus t by t into R by L, or you can write it as V by R 1 minus e power minus t by tau. For RL circuit, the time constant is L by R. So tau value is L by R. L by R. Are you understanding? So now voltage drop across the capacitor, inductor. So VL is equal to L di by dt. So VL is equal to L into d by dt of your current V by R 1 minus e power minus t by tau. So if you substitute, finally you can get V e power minus t by tau. By differentiation, you are getting the equation 6 as voltage drop across the inductor. So that is V into e power minus t by tau. So here the current is what value? V by R 1 minus e power minus t by tau, and the voltage drop across the inductor value is V e power minus t by tau. So here if you substitute t is equal to 0, so finally the current will be starts at 0. The current will be starts at 0, and gradually the time increases. The current value is also increases up to a maximum limit of V by R. Up to a maximum limit of V by R. So that is one time constant. So similarly, voltage drop across the inductor. So the equation is V e power minus t by tau. So it is exponentially decaying. So t is equal to 0. So it is maximum value of V by R, and the time is go on increasing. It is gradually comes to 0 position. 0 position. So now for one time constant, so what is the time constant of RL circuit? So the time constant can be recorded as the time required for the transient response to attain 36.78% of your initial value. So that is from the value of VL, it reaches to 36.73%. So like this you can get. So this is the value. So 36.78%. So under that condition, the tau value, this is your tau value. So the tau value is L by R. So are you understand this? So similarly, I am going for the Laplace transform. Here the same thing only. RL are connected in series, is excited by a step response of V volts. At t is equal to 0, the switch K will be closed and a current will flow through the circuit. So assume that the inductor has no initial value of currents. So t is equal to 0 minus I of 0 minus is 0. T is equal to 0 plus I of 0 plus is also 0. So apply the KVL for writing the equilibrium equation. So R into I, voltage drop across the resistor, L into di by dt, voltage drop across the inductor, is equal to V, applied voltage. Taking Laplace transform, so R into I of S plus Ls into I of S is equal to V of S by S. So the given excitation is a step excitation. So that's why V of S by S. So now I am taking I of S as common. R plus L of S into I of S is equal to V of S by S. Then I am taking L as common. So L into R plus R by L plus S into I of S is equal to V of S by S, or L into R by L into S, I of S is equal to V of S by S. So then I of S is equal to V of S by L divided by S plus R by L, S plus R by L. So here by taking the S and S plus R by L, you have to go for the partial fraction. So if you go for the partial fraction, so you can get I of S is equal to V of S by R into 1 by S minus 1 by S plus R by L. So then take inverse Laplace transform. So you can get I of t is equal to V by R plus the value of A, e power minus R by L into t. So anyway, the value of A will be getting as minus V by R only. Minus V by R only. Are you understand this? Then come to RLC series circuit. So R, L, C are connected in series. Inductor has no initial current. Capacitor has no initial voltage. So it is excited by a step response of V volts. So at t is equal to 0, the switch will be closed. A current I of t will flow through the circuit. Okay. So here at t is equal to 0 means two conditions you can get. So one is t is equal to 0 minus condition. Another one is t is equal to 0 plus condition. Just before the switch is closing position is t is equal to 0 minus. So under that, so I of 0 minus is 0 only. So because the circuit is still open, no current will flow to the circuit. As well as the voltage drop across the capacitor is also 0. No current, no voltage drop across the capacitor. Then at t is equal to 0 plus condition, so just immediately the switch is closed position. The inductor never takes the instantaneous currents, it will be open circuited. The capacitor never takes the instantaneous voltages, it will be short circuited. So I of 0 plus is 0, VC of 0 plus is also 0. Then coming to the equilibrium equation by using KVL application. So voltage drop across the resistor is R into I. Inductor drop is L di by dt. Capacitor drop is 1 by C integral I dt is equal to V. So Ri plus L di by dt plus 1 by C integral I dt is equal to V. So this is your equilibrium equation. So here integration is there. So to avoid the complexity, we have to go for differentiation with respect to t. So R into di of t by dt plus L into d square I by dt plus 1 by C into I is equal to 0, because the supply voltage is a step constant of V volts, derivative of constant is 0. So then d square I of t by d I square of t by dt square plus R by L di by dt plus 1 by LC into I is equal to 0. So that is d square plus R by L d plus 1 by LC into I is equal to 0. So this is a second order differential equation. So to go for the second order differential equation, so the basic solution of the equation is I is equal to some constant A e power m1t plus some constant b e power m2t, where m1 and m2 are the roots of the basic equation d square plus r by l d plus 1 by lc, and a and b you can get by applying the initial conditions. So at t is equal to 0 plus condition, then you can get the values of a and the value of b. Are you understanding? So for the characteristic equation, d square plus r by l into d plus 1 by lc is equal to 0, then the roots of the equation is like this. So m1 m2 as minus r by l plus or minus root of r by l square minus 4 into 1 by lc divided by 2, or you can write it as minus r by 2l plus or minus root of r by 2l whole square minus 1 by lc. So these are the roots of the equation. So in this you have to go for a good discussion with respect to the roots, because the roots may be real, may be non-equal, may be complex conjugates. According to that, there are three damping values you can get: under damped, critically damped, over damped conditions you can get for the equations. So to understand this, under the radical r by 2l whole square minus 1 by lc, so we are going for the calculation. If the first case is root of r by 2l whole square minus 1 by lc is positive, so when you can get this is positive, r by 2l whole square is always greater than 1 by lc. So then the roots are negative real. Then the roots are negative real. So under that condition, you can get a overdamped condition. Overdamped condition. Okay. So then if the radical root of r by 2l whole square minus 1 by lc is equal to 0. So how you can get r by 2l whole square must be equal to 1 by lc. So then the roots are equal. So you can get minus r by 2l. The roots are equal m1 and m2. You can get minus r by 2l. Okay. So this is called the overshoot condition with respect to critically damped condition. Overshoot condition with respect to critically damped condition. And the last case is the under the radical r by 2l whole square minus 1 by lc is negative. So when you can get is negative, r by 2l whole square is less than 1 by lc condition, then you can get a complex conjugates of roots m1 and m2. So this condition you can call it as a underdamped condition. So for this one, to go for the different cases of responses, so the first case is your overdamped condition. So it is a sluggish system. It is a sluggish system. So sluggish means you can get the steady state value after a long time. After a long time. And coming to the second case, the roots are equal condition. So you can get the response is very fast with less overshoots. With less overshoots. And while you are going for the third case, the complex conjugate roots, you can get a oscillations. You can get a oscillations and reaches the state of stability for a certain time. So these are the three cases you are getting. So the overall expression in time domain behavior can be represented as d square I by dt square plus 2 zeta omega n into di by dt plus omega n square into I is equal to 0, where omega n is the natural frequency of the system. Natural frequency of the system, and zeta is the damping ratio. Zeta is the damping ratio. So finally the roots can be represented as m1 m2 minus zeta omega n plus or minus omega n root of zeta square minus 1. So the I of t value can be represented as a e power minus zeta omega n plus omega n root of zeta square minus 1 into t plus b into e power minus zeta omega n minus omega n root of zeta square minus 1 into t. So m1 and m2 values. Are you understanding? So for a critically damped condition, the roots must be equal and the response must be very fast with less overshoots. Less overshoots. Are you understanding? So like this you have to go for the RLC series circuit final solution with respect to second order differential equation with complementary function as well as the particular integral. So while you are coming to S domain, so the same thing only, circuit is not changed. R, L and C are connected in series with a step excitation of V volts. A current will flow through circuit after the switch is closed at t is equal to 0. So the initial conditions, I of 0 minus condition, inductor current is 0, capacitor voltage is also 0. So at t is equal to 0 plus, inductor never takes the instantaneous currents and capacitor never takes the instantaneous voltages. So IL of 0 plus is 0, VC of 0 plus is also 0. Apply the KVL, so you can get voltage drop across the resistor is R into I of t, voltage drop across the inductor is L into di of t by dt, and voltage drop across the capacitor is 1 by C integral I dt is equal to your applied voltage V. So now taking Laplace transform, so R into I of s plus Ls into I of s plus 1 by C I of s by s is equal to V of s by s. Okay, so taking R plus Ls plus 1 by Cs into I of s is equal to V of s by s. So I am taking Cs as LCM. So RCS plus LCS square plus 1 divided by Cs into I of s is equal to V of s by s. Then I am taking LC as common. So s square plus R by L into s plus 1 by LC divided by Cs into I of s is equal to V of s by s. Then I of s is equal to V of s by s into Cs divided by s square plus R by L into s plus 1 by LC into LC. So here the C and CR gets cancelled, S and SR gets cancelled. So V of s by L divided by s square plus R by L into s plus 1 by LC. So now I am going for the second order equation as s minus m1 into s minus m2. So the roots of the equation already you are getting for the basic equation of your time domain analysis also. So that is minus r by 2l plus or minus root of r by 2l whole square minus 1 by lc. So the complete solution can be represented as I is equal to a e power m1t plus b e power m2t. So like that you have to go for the solution of RLC series circuit under DC excitation. So these are the important things. So for a RL circuit, you are getting a time constant that is L by R. For a RC circuit, you are getting a time constant that is R into C. So in the case of RLC series circuit, so you are getting different damping coefficients. So underdamped, overdamped and critically damped conditions. So generally the roots are equal and opposite. Then you can get the roots are equal, then you can get a critically damped condition. So negative roots are there, over damped condition, complex roots are there, under damped condition you can get. Okay, so now we are going for analyzation of RC circuit using AC excitation. So in AC excitation, I am taking the voltage V of t is equal to Vm sin omega t plus theta. V of t sin omega t plus theta. So R and C are connected in series. A current of I of t will flow through the circuit at t is equal to 0. The switch K will be closed position. So here I am assuming that the capacitor has no initial charge. So under that condition, so you can get two switching instants at t is equal to 0 minus just before the switch is closed position, and at t is equal to 0 plus just immediately the switch is closed position. So now at t is equal to 0 minus, so voltage drop across the capacitor is 0 because no current will flow to the circuit, still it is open path. And at t is equal to 0 plus condition, so the capacitor never takes the instantaneous currents, so it acts like a short circuit. So the voltage drop across the capacitor V of 0 plus is also 0. So then apply the KVL for writing the equilibrium equation. Voltage drop across the resistor is R into I. Voltage drop across the capacitor is 1 by C integral I dt. And your applied voltage V of t is Vm sin omega t plus theta. So that is your first equation. Ri plus 1 by C integral I dt is equal to Vm sin omega t plus theta. So here the integration is there. So the complexity will be there. To avoid that, we are going for the differentiation with respect to t. So then you can get R di by dt plus 1 by C into I is equal to Vm sin omega t plus theta. Differentiation is cos omega t and omega t differentiation is omega. So finally you can get Vm omega cos omega t plus theta. So now di by dt plus 1 by RC into I is equal to Vm omega by R cos omega t plus theta. So capital D plus 1 by RC into I is equal to Vm omega by R cos omega t plus theta. So this is a first order equation, but it has complementary function as well as particular integral. So the complementary function of the equation is some constant k1 e power minus t by rc. So why we are getting d plus 1 by rc is the value. So the complementary function is, so I of I suffix t is equal to k1 e power minus t by rc. So that is k1 e power minus t by tau, where tau is r into c. It is a time constant for RC circuit. Then while we are going for the complementary function, particular integral, so I am taking IP is a steady state current. So the solution for this is A cos omega t plus theta plus B sin omega t plus theta. So if you differentiate with respect to t, so d ip by dt is equal to minus A sin omega t plus theta into omega plus B cos omega t plus theta into omega, or you can write it as minus A omega sin theta sin omega t plus theta plus B omega cos omega t plus theta. Okay, so now we are substituting this current value. Now we are substituting this current value in your equation 2 as di by dt and I value also. So if you substitute, you can get R into, so what is that? R into di by dt. So dip by dt value you have to write minus A omega sin omega t plus theta plus B omega cos omega t plus theta plus 1 by C I value A cos omega t plus theta plus B sin omega t plus theta, that is equal to Vm omega cos theta. So then you are segregating the sine terms and cosine terms. So B by C minus A r omega into sin omega t plus theta, Br omega plus A by C into cos omega t plus theta is equal to Vm sin omega t plus theta. Now comparing the LHS and RHS, so you don't have any sin omega t plus theta in the RHS side. So that means B by C minus AR omega is equal to 0. So AR omega is equal to B by C, or A is equal to B by RC into omega. So similarly, cos omega t plus theta terms here comparing, Br omega plus A by C is equal to Vm omega. So Br omega plus B by RC square omega is equal to Vm omega. So I am substituting the A value as B by RC omega, equation 5. Okay, so then B into r square c square omega square plus 1 divided by rc square omega is equal to Vm omega. So that implies B is equal to Vm r c square omega square divided by r square c square omega square plus 1, or B is equal to, after simplification by cancellation and taking equal parts, so Vm r by r square plus 1 by c square omega square. So once you are getting the B value, so this B value you can substitute, you can get the value of A. What is A? A is B by RC omega. So B is Vm r by r square plus 1 by c square omega. So finally you can get A is equal to Vm divided by c omega into r square plus 1 by c square omega square. So A value are calculated, B value are calculated. Therefore the steady state current is equal to, or the particular integral current is equal to Vm by c omega into r square plus 1 by c square omega square cos omega t plus theta, Vm r by r square plus 1 by c square omega square sin omega t plus theta. So then taking the common, so Vm by r square plus 1 by c square omega square cos omega t plus theta divided by c omega plus r into sin omega t plus theta. So this is your steady state current or particular integral current. Still, I am taking the denominator value under the roots. So the steady state current will be like this, equation 7. So ISS is equal to Vm by root of r square plus 1 by c square omega square cos omega t plus theta divided by c omega into root of r square plus 1 by c square omega square plus r into sin omega t plus theta divided by root of r square plus c square omega square. So why I am taking this equation means I have to represent in terms of impedance. I have to represent in terms of impedance. Okay. So now the impedance triangle for RC circuit is horizontal is resistance. Horizontal is resistance. So vertical is capacitance. So the hypotenuse is your impedance value. So impedance is root of r square plus 1 by c square omega square. So cos phi value is r by root of r square plus 1 by c square omega square. Sin phi value is 1 by c omega divided by root of r square plus 1 by c square omega square. We are obtained from the impedance diagram. We are obtained from the impedance diagram. Okay. So now what is cos phi r divided by root of r square plus 1 by c square omega square, and sin phi value is 1 by c omega divided by root of r square plus 1 by c square omega square. Now we are substituting the values. So here the root with c omega r by root values are there. I am replacing with respect to this. So ISS is equal to Vm divided by root of r square plus 1 by c square omega square. So sin phi cos omega t plus theta plus cos phi sin omega t plus theta. So it is sin A cos B plus cos A sin B. So finally the steady state current ISS is equal to Vm divided by root of r square plus 1 by c square omega square sin omega t plus theta plus phi. So what is phi? Phi is tan inverse of 1 by c omega into r. 1 by c omega into r. And what is root of r square plus 1 by c square omega? It is magnitude of z only. So finally the current value you can get it as Vm by z sin omega t plus theta plus phi. So that is your steady state current value. So now the complete solution is the natural response and forced response. So that is the transient current and steady state current. So I of t is equal to some k e power minus t by tau plus Vm by z sin omega t plus theta plus phi. So for finding the value of k, we have to substitute the initial conditions. So at t is equal to 0 plus the voltage drop across the capacitor is 0. The voltage drop across the capacitor is 0 means it is short circuited. So it is short circuited. So which means only resistance is present in the circuit. So what is the current you can get? So I is equal to V of t by R. So from that you are writing the expression. So that is R into I is equal to Vm sin theta. So t is 0 condition, omega t is 0. So finally you can get sin theta only. So I of 0 plus is equal to Vm by R sin theta. So that is the value you are getting. So now Vm by R sin theta is equal to K1. So e power minus 0 is 1. Vm by Z sin omega t is 0 plus theta plus phi. So Z is equal to root of r square plus 1 by c square omega square. Phi is tan inverse of 1 by omega c r. So k is equal to Vm by r sin theta minus Vm by Z sin theta plus phi. So finally, the complete solution is the transient value is Vm by R sin theta minus Vm by Z sin theta plus phi e power minus t by tau, and the steady state current is Vm by Z sin omega t plus theta plus phi is the overall response. So like this, you have to go for the calculation of the sinusoidal excitation is applied to a RC circuit. So similarly, while we are coming to the RL circuit, so here also have taken the assumption that no inductor current initially appeared due to the previous source. So the inductor is under relaxed position. R and L are connected in series. I am taking the excitation voltage V of t is equal to Vm sin omega t plus theta. At t is equal to 0, the switch will be closed and a current of I of t amperes will flow through the circuit. So the t is equal to 0. We are getting the two conditions. So t is equal to 0 minus condition just before the switch is closed position. So still the circuit is open path. The current flowing through the inductor is 0. So at t is equal to 0 plus, the switch is immediately closed position. Inductor never takes the instantaneous currents. So the inductor current is 0. So now apply the KVL for the circuit under closing of the switch. So voltage drop across the resistor is R into I. Voltage drop across the inductor is L di by dt. So your applied voltage is V of t, that is Vm sin omega t plus theta. So finally you can get Ri plus L di by dt is equal to Vm sin omega t plus theta. So di by dt is equal to R by L into I is equal to Vm by L sin omega t plus theta. So capital D plus R by L into I is equal to Vm by L sin omega t plus theta. So it is a first order differential equation, but the right hand side is a sine function is there. So we are getting complementary function as well as your particular integral. So the particular complementary function is transient response. So the transient current I suffix t is equal to some constant k2 e power minus R by L into t, or k2 e power minus t by tau, where tau is L by R. It is a time constant for RL circuit. Then for finding the particular integral, so I am going for IP as a cos omega t plus theta plus b sin omega t plus theta. So for first order differential equations, we have to go for the function a cos omega t plus theta plus b sin omega t plus theta. I am differentiating with respect to t. Dip by dt is equal to minus a omega sin omega t plus theta plus b omega cos omega t plus theta. So now substituting these two values in your equation 3. So if you substitute in your equation 3, r into a cos omega t plus theta plus b sin omega t plus theta. So not in equation 3, equation 2. In equation 2. Okay. So r into a cos omega t plus theta plus b sin omega t plus theta plus L into minus a omega sin omega t plus theta plus b omega cos omega t plus theta is equal to Vm sin omega t. So now I am subgregating the sine terms and cosine terms. So Vr minus Al omega into sin omega t plus theta, Ar plus Bl omega cos omega t plus theta is equal to Vm sin omega t plus theta. So in right hand side you don't have any cos functions. By comparing LHS and RHS, the cos term right hand side is 0. While you are coming to the sine functions, both sides you are having. So Br minus Ar L omega is equal to Vm, and similarly for cos function Ar plus Bl omega is equal to 0. So Ar plus Bl omega is equal to 0. So A is equal to minus Bl omega by R. And similarly for sine function Br minus Al omega is equal to Vm. So Br plus, I am substituting the A value from the above equation, Bl square omega square by R is equal to Vm. So that implies I am taking the B with a R square plus L square omega square by R by taking the LCM. So you can get the value of RHS is Vm only. Then B is equal to Vm R by r square plus L square plus omega square. So B value are calculated. Substitute the B value for finding the value of A. So for finding the value of A, so A is equal to minus Vm R L omega divided by R into R square plus L square omega square, or Vm L omega by R square plus L square plus omega square. So once you are calculated the A and B value, the steady state current or your particular integral current ISS is equal to Vm by R square plus L square omega square R into sin omega t plus theta minus omega L into cos omega t plus theta. So now the R square plus L square omega square, I can write it as root of R square plus L square omega square into root of R square plus L square omega square. Then the steady state current Vm by root of R square plus L square omega square into R by root of R square plus L square omega square into sin omega t plus theta minus Lm root of R square plus L square omega square cos omega t into theta. So here I am writing these values by using your impedance triangle of RL circuit. Impedance triangle of RL circuit. So the impedance triangle of RL circuit, horizontal is resistance, vertical is L omega, hypotenuse is Z. So Z is equal to root of R square plus L square omega square. So by using this impedance triangle, cos phi is R by root of R square plus L square omega square. Sin phi is L omega root of R square plus L square omega square. Then ISS is equal to Vm divided by root of R square plus L square omega square cos phi sin omega t plus theta minus sin phi cos omega t plus theta. Or you can write it as cos A sin B minus sin A cos B. So Vm divided by root of R square plus L square omega square sin omega t plus theta minus phi, where phi is tan inverse of L omega by R. And what is Z? Z is magnitude value root of R square plus L square omega square. So finally the current value you are getting as Vm by Z sin omega t plus theta minus phi, or ISS is equal to Vm by Z sin omega t plus theta minus phi. So here it is a lagging angle because of inductance. In the case of capacitance you are getting plus phi because of leading. So I is equal to natural response plus forced response k2 e power minus r by L into t Vm by Z sin omega t plus theta minus phi. For finding the value of k2, so we have to apply the initial condition at t is equal to 0 plus condition. So that is I of 0 is 0, 0 is equal to k2, e power 0 is 1, Vm by Z sin of omega t, t is 0, omega t is 0 plus theta minus phi. So finally k2 is equal to minus Vm by Z sin theta minus phi. So I of t is equal to Vm by Z sin omega t plus theta minus phi minus sin omega t minus phi e power minus t by tau. So that is the equation you are getting for a RL circuit. And finally come to the RLC series circuit. So here RLC are connected in series with a excitation of V of t is equal to Vm sin omega t plus theta. So a current will flow through the circuit at t is equal to 0 condition. Once the switch is closed, the current will flow through the circuit. So here you can get the two switching instants, t is equal to 0 minus. So just before the switch is closed position, no current will flow through the circuit. The inductor current is 0. The capacitor voltage drop is also 0, because we are assuming the inductor and capacitor are under relaxed condition. Then at t is equal to 0 plus condition, so the switch is immediately closed position. Inductor never takes the instantaneous currents, capacitor never takes the instantaneous voltages. So the current value of inductor is 0, the capacitor voltage drop is also 0. Now apply the KVL for this loop. So the equilibrium equation is R into I L di by dt 1 by c integral I dt is equal to Vm sin omega t plus theta. So here integration is there. To avoid the complexity, we are going for the differentiation. So r di by dt plus L d square I by dt square plus 1 by ci is equal to Vm omega cos omega t plus theta. So d I square divided by dt square plus r by L di by dt plus 1 by LC into I is equal to Vm omega cos omega t divided by L. So then d by dt I am writing as capital D. So d square plus r by L into d plus 1 by LC into I is equal to Vm omega by L cos omega t plus theta. So for this also it is a second order differential equation. You are having complementary function as well as the particular integral. So the particular integral we are finding IP is equal to A cos omega t plus theta plus B sin omega t plus theta. Then dip by dt, differentiating the IP value with respect to t. So you can get minus A omega sin omega t plus theta plus B omega cos omega t plus theta. So d square means dip square divided by dt square. So you can get minus A omega square cos omega t plus theta minus B omega square sin omega t plus theta. So substituting all these values in your original equation, then you have to go for the solution for the particular integral. So you can get the final value as ISS is equal to some constant into sin phi cos omega t plus theta plus some constant into cos phi sin omega t plus theta, or m into that constant m into sin omega t plus theta, where m is root of m square plus cos square phi plus m square sin square phi. So that value is the m value, and phi value is tan inverse of 1 by r 1 by LC minus L omega. So like that you have to go for the calculation of the values of your m. Okay. So by substituting the value of m, finally you are getting Vm divided by root of r square plus 1 by c omega minus L omega square. So the steady state current or particular integral current IP is equal to Vm by Z, where Z is root of r square plus 1 by c square c omega minus L omega whole square sin omega t plus theta plus phi. So if you take leading angle, so if you are getting minus phi, it is a lagging angle. So inductiveness is more, you can get a lagging angle. So capacitiveness is big, you can get a leading angle. Okay. So after that you have to go for the overdamped condition under the radical. We are checking. So r by 2l whole square must be greater than 1 by LC. So negative real values you can get. So for that you can get the overall expression I is equal to e power alpha t, some constant c1 e power beta t plus c2 some constant e power minus beta t plus Vm by Z sin omega t plus theta plus phi. So if the roots are having same, so that is r by 2l whole square is equal to 1 by LC. So it is a critically damped condition. So you can get e power alpha t c1 plus c2 t plus Vm by Z sin omega t plus theta minus phi. So if it is under damped condition, that is complex conjugates are there. So the overall response I is equal to e power alpha t. So some constant c1 cos beta t plus some constant c2 sin beta t plus Vm by Z sin omega t plus theta plus phi. So like that you have to go for the calculations of the different response values of damping conditions for a sinusoidally excitation system. Thank you, one and all.